For the second part of the lab session, we will address how to disseminate this pseudorandom sequence. And here so far we've generated the spectrum spreading signal by using a noise source, and noise source cannot be shared between multiple users. So we need a way of identifying what is the random sequence so that a user can generate this sequence locally and have the fine timing capability. So this is what gold codes are. Gold codes are the pseudo-random sequence 1023 bit long, published by the US Air Force, and which is used in GPS receivers to have a local copy of the sequence and have an accurate timing capability. So we will not get into the fancy gold codes. We will make it very simpler, and we will show how easy it is to create this pseudo-random sequence using linear feedback shift registers and XOR functions, and by watching how these two pseudo-random sequences will correlate if they match and not correlate if they do not match. What are pseudo-random sequences? What can be demonstrated using this Galois linear feedback shift register GLFSR is that if we have these shift registers, and at each clock cycle all these bits located in the shift register will be shifted by one position to the right. So this 0 will be moving over here, this 1 will be moving over here, this 0 will drop in vacuum, and at each new clock cycle the shift register will shift its content. A new bit will enter the shift register, and this new bit is the XOR, the exclusive OR, between two taps. These taps are the feed position of these two shift register positions over here. So if you remember what the XOR function looks like, if I consider the XOR truth table, if I have 0 and 1 as one input, 0 and 1 as the other input, we see here that 0 XOR 0 is 0, 1 XOR 0 is 1, 0 XOR 1 is 1, and the originality of XOR is that 1 XOR 1 is 0. So this is the same as an addition with the carry function. 1 plus 0 is 1, 0 plus 0 is 0, and 1 plus 1 is 0 with a carry. So XOR is this truth table which will define the input here. And if you select wisely the tap functions, you can demonstrate that this sequence will not repeat any sooner than the length 2 to the n minus 1 for the n long shift register. So here are two examples of GLFSR as found in two out of the 18 possible 7-bit long LFSR. This is 7-bit long over here. So this reference cites all the possible tap positions that will create these pseudo-random sequences, and these are two sequences that will be used in this lab session. So what we see here is that we have tap positions 7 and 4, we have tap positions 7 and 6, and by expressing these as a polynomial expression, the algebra of this polynomial division allows us to demonstrate that the sequence will never repeat before 2 to the n minus 1 with n equals 7, that's 127. So such a circuit is actually quite easy to implement in electronics. So in electronics, this will be made of a linear shift register here, the shift register with its outputs. Here we have 8 outputs, 7 of which are used. And we see here that we have this XOR function which feeds back the output of two tap positions. These two tap positions can be selected using a switch, so that we have the two possible declinations of this linear feedback shift register, and we have here a trigger signal which is the end, not end, of all the outputs of the shift register, so that when we go through the all one state, we will have a 0 output over here, which is a trigger function to remember that the whole cycle is starting again. This is repeated twice for one linear feedback shift register, a second linear feedback shift register, and then the output of these two LFSR must be mixed to detect the correlation. So again, remember the correlation is this function where we first multiply the two terms. So the correlation will be something like the cross correlation between these two signals will be the integral of the product of one signal at time t multiplied by signal 2 at time t plus tau. And this must be integrated over time dt. So how do we actually implement this? Well, again, by using a XOR function, we have something that reminds us of a multiplication. Remember, the XOR will be something that says if I have 0, 1 as an input and 0, 1 on the other input, then I will create 0, 1, 1, 0, so that if the two LFSR here are not matching, the two inputs of a XOR function will be either 0 or 1. So if they are above 0, we will output 0. If they are above 1, we will output 0. But if they are 1 or 0 or 0 and 1, we will output 1. So on the average, we will create something of 0.5, half mean value. If, however, the two sequences match, we see that 0 and 0 will create 0. All 1 and 1's matching will create a 1 and 1 XOR 1 will create a 0, and all values will add up as 0. So we have this multiplication here, which is taken care of by this XOR function. If pattern 1 and pattern 2 match, then all the 0 will match with 0, creating an output at 0. All the 1s will match the 1s with an output at 0, and the output of this multiplication of all the terms will be all zeros. How do we integrate over time? This is this low-pass filter over here. So this low-pass filter will be the integral over time here. So we do a multiplication using the XOR, and the output will be low-pass filtered, and this is the integral dt. So the actual hardware implementation of the integral of S1 times S2 is taken care of by this XOR function and its low-pass filter. So let's look at how this signal looks like on the practical output. So here is our implementation of a circuit. You see here one circuit with the feedback shift register. The shift register here is the XOR. This is duplicated. Here we have a switch that allows us to select one or the other sequence, and then we have here the XOR output with its low-pass filter that will allow us to detect the correlation. So if we consider the output of this sequence here, we need to have a way of creating the tau offset of this tau offset over here. How do we create the tau offset? Well, actually, we're going to feed these two LFSR sequences with the audio output of a computer used as a signal generator, and the two signals of a stereo output. So it's a coherent sound card because both outputs are clocked from the same local oscillator, and we create a slight offset in the frequency feeding these two feedback shift register. How do we do this? Of course, using new radio. So here is the flowchart that was prepared. We simply take two signal sources clocked at 48 kilosample per second. This is the frequency feeding the sound card, and we clock on the one hand at 21 kilohertz as sound output, on the other hand at 21.1 kilohertz. So this is a 100 hertz frequency offset, and we take an audio sync with two inputs so that we have a stereo input in generating this signal. So if I display again the oscilloscope output at the same time as GNU Radio here, and if I start playing the signal, what we see here on the oscilloscope is on this yellow curve here we have the pseudorandom sequence. on the blue curve here, we have the first trigger signal. So this all NAND output over here is the trigger signal that is visible for the first pseudorandom sequence generator over here, and in purple on top is the output of the second generator, which is over here. So we see that these two trigger signals are drifting one with respect to the other because the two clock signals are slightly offset. And finally, we have over here the output of a low-pass filter, which is the blue curve here on the bottom. So now let us trigger on this low-pass filter output. So if I take the trigger signal and set it to normal mode over here, now what we see here is that whenever the two sequences match, indeed, instead of having a mean value of 0.5, half the voltage, which is the mean value of 0, 1, or 1, 1, and 0, 0 at the XOR output, we see that when the two patterns match, all the XOR output will be 0 and the average will be 0. So we see this dip on the signal. If now I change the second pseudorandom sequence to the other sequence, there is no correlation peak, so I need to go back to auto mode. And what we see here is that now the two pseudorandom sequences do not match and there is no correlation peak anymore. If I go back to the original sequence and back to normal, then I have a correlation peak again. So you see how easy it is to generate using these linear feedback shift register with the appropriate tap positions, which can be easily shared between users. If I define the length and the tap position, I have defined all the parameters of the communication scheme. Now, unfortunately, you do not have access to this circuit, so let us try and see how we can simulate this setup using GNU Radio. So back to GNU Radio, we create a new Qt graphical interface chart, and we shall call this new example lab 02 to start working. GNU Radio is provided with the GLFSR source, so we can actually select the first linear feedback shift register, and we are told here that we can select the degree, so how many taps, how many positions in the shift register, and documentation tells us that the mask allows us for defining the feedback pattern, so basically where the taps are located. So first of all, we have degree 7. This is simple enough because it's the number of cells in the shift register, and now we need to define the mask. So to create the mask, we have seen that we have two positions of the taps, 7 and 4 or 7 and 6, and because we start indexes from 0, we need to use the mask as 2 to the, so position 7 starting from 0 is 2 to the 6 plus 2 to the 3 for position 4, so that will be the mask 72, or if you're more familiar with hexadecimal display, that would be 0x48. So if I double click over here, I can give the mask, and the mask will be 0x48. That's my first linear feedback shift register. The second one will be 2 to the 6 plus 2 to the 5. So that will be the pattern at the 7th position and the 6th position, that's 0x60. So if I copy this GLFSR and I set this time to 0x60, I get my two linear feedback shift registers. The next step will be exactly the same as before. We're going to take the Fourier transform, but this time not of the complex but the float. We select a variable n, the number of terms in the Fourier transform, and we create a variable with n, the length of the correlation, which again is equivalent to the pulse repetition interval in a radar system, how often the pulse are emitted. We need to convert the stream to vector, so stream to vector over here with length n, and we need to remember to introduce a throttle block somewhere to slow down the data rate. So this is going to be introduced over here. This is again a sequence of n elements, so this will be acting on floating point numbers, and the stream to vector acts on float as well. So here is our first sequence, and then we've got, once we've performed the Fourier transform, we need to multiply with a complex conjugate, again on a sequence of n elements and not a single one. And finally, when we have completed this operation, we take the Fourier transform, and we've seen that to be consistent we need first to reverse, then to forward with a length n of the number of elements that we're handling over here. So we take this guy over here, input over here, we duplicate all these elements that need to be introduced on the second path over here, and finally we can conclude this flowchart by displaying the magnitude of the output, so complex to magnitude, after having converted the vector back to streams on the length n elements, and we display the output on an oscilloscope output, so we simply take the time sync of the queued graphical user interface, this time displaying floating point numbers. So again, length n to make sure that we have the right number of data. So if I run this sequence here, well, initially I've selected, so again I save this as a sequence in a writable directory, that's lab number 2, and when I save this chart I can execute, and I autoscale middle button to display the results. Here we see that there is no correlation peak. Of course there is no correlation peak because we have selected two different LFSR, pattern 72, pattern 96. So if we now select the same one, and if we can try to remember which are the two values by putting comments, so the comment is 0x48 or 0x60 as the two possible values. So now we remember what values are, and we will select here 48 as the pattern, and to make sure that we increase a bit the refresh rate of the output, we can increase the data rate. So here we execute, and if we autoscale, what we see now is we've got this first guy over here at offset. Well, that's not very convenient because the millisecond is a time that is not integer, so let's make it every 1 is 6, so that we make it in microseconds, and that will make it easier to read. If we now autoscale middle button, we see that the first here is at 3 microseconds, but the second is at 130, so that's indeed 127 tap long, so that's the number of elements. Then we have 256 here, so this is the length of the pseudorandom sequence of a degree here. So if we have the same pattern, we see that they repeat. This is actually the shape of the windowing function in the Fourier transform that we have here. We have this Blackman-Harris windowing function, and that's the correlation weighting function here. These are these correlation peaks here. So again, if we take different patterns, we see that they will not repeat, and there will be no coherence peak between these two functions here. So the last item that must be fruitful to analyze is what is the individual spectra shape. So to do this, we introduce a spectrum analyzer that's a queued graphical interface frequency sync, and actually we need only a single frequency sync with two inputs so that we can compare these two guys over here. So we can have a two-channel spectral analyzer displaying the properties of a floating point number, and thanks to this block here, we can address the shape of the spectra of these pseudorandom sequences. So remember, pseudorandom sequences are noise, so a noise source is expected to be flat. And surely enough, if we execute this flowchart, we see here, if I autoscale, that both sequences do not correlate, and yet both sequences, we see here that the two spectra overlap, red and blue are exactly the same. The spectrum are flat. So the flat spectrum means that we have a noise with no repeating sequence, and on the correlation here we have no correlation peak if we run the two different sequences. If I run the same sequence on both paths, then again I will have a flat spectrum, and yet this time I will get correlation peaks every 127 samples, because here I'm going at 1 megasample per second. So flat spectrum in the frequency domain, and correlations every 127 samples. So this allows you to repeat the demonstration by yourself on your copy of New Radio, and this is what we just demonstrated. So flat spectra here on the same scale, correlation peaks every 127 or every 2 to the n minus 1 samples, and with different pseudorandom sequences we have no correlation peaks. So if you have access to the analog copy of this experiment that we just did, if you take a Hewlett-Packard 3562 dynamic signalizer, you can have the same output as we just displayed using New Radio. On this example here, you see the flat spectrum of each individual PRN generator. Actually, it's a flat spectrum with discrete time sampling, because we are clocking. If you remember, in this example, we were clocking the linear feedback shift register at 21 kilohertz. So the notch here, this is the sync, the cardinal sync function, sine function, which is due to the discrete clocking the system, but this is a flat spectrum for each individual pseudorandom sequence generator. So this proves the flat spectrum, that it is indeed pseudorandom. But if we take the correlation, so this is achievable by using the cross-correlation function of this instrument, you find this cross-correlation which is separated by the frequency difference between the two generators multiplied by 127 the length of the code. So if you have two very close frequencies, these correlation peaks will be widely spaced apart. The further away the two frequencies, the more often these two correlation peaks will appear. So because tau is flowing more quickly if you have a larger difference. So this concludes the presentation about pseudorandom generators and pseudorandom sequences. And now we have all the information to get started with GPS decoding. So make sure that throughout this lab session, the previous part has been well understood before continuing with the last step of GPS decoding.